I was going to spend some time talking about applications of Extrema and using all of our tools that we've learned to solve some problems, but I thought it might just be simpler to go ahead and present some problems, solve them, and talk a little bit about the techniques we need along the way. So I want to start off here by saying, all right, we've got some point in space, -2, -2, 0, and we have some sort of surface, and we want to find a way to minimize the distance there. We want to find the distance from this point to that point. Because if it's a surface, let's say it's a surface that goes down like this, and there's a point in space. Well, there's a direct line that hits it, but there might be some sort of not skew line, but some sort of line that's offsetting that still hits the surface. But we want to find the minimum distance from that point to the surface. So to do that, we need to be a little bit clever. So if you remember, the distance formula tells us that we have to take the differences in the points. Let's take the differences in the points, square them, and take the square root. And we want to minimize the distance between this and that. But there's a trick. And the trick is that if this is minimized, then there's another function this function is also minimized, right? Because the square root just takes the square root of this. If this is small, the square root, I'll put it this way, if one distance is less than the other, the square root of that distance will still be less than the other. So instead of worrying about this function, let's worry about this function. And so what we have to do is there's some point on the surface. We'll call that point, some point x, y, z. And the distance between that and the surface we're trying to minimize. So the way that we construct that is I'm gonna call this f. It's that x minus the point plus y minus the point plus z minus the point. So really we're trying to find the x, y, z that minimizes this equation, that makes the output of this the smallest. So we have x and y, but if you look at this, z is actually defined in terms of x and y. So I could just say x plus 2 squared plus y plus 2 squared plus the square root of 1 minus 2x minus 2y squared. So then if I keep going with that, now I'm in a particular case where I've got a function of two variables and I want to find a minimum. So this is just like what we did before. We can work with the surface. We can say, all right, I need the partial with respect to x. All right, so I take that goes away, those go away, and I have this. All right. So now I have 2x plus 2 and 2y plus 2. So I need these to be set equal to 0. Well, there's no x and y aren't both in here, so we get off easy. We can just solve for each one individually. X and Y are -1. So then we need to make sure this isn't somehow a maximum. So we should really go further. We should really get f double prime, or rather partial with respect to x twice, and the mixed partial is 0. So that tells me d is 4, which is greater than 0. Since that's positive and that's positive, that tells me that we're dealing with a minimum. So ultimately, we have this point. Whatever x is, whatever y is, and then we need to get the z coordinate. So that's 1 plus 2 plus 2 again is the square root of 5. But we need to find the distance from this to here. So then we got to keep going. Our distance then is, right, we got to go all the way back to this function. We got to say -2 plus 1 squared plus -2 plus 1 squared plus 0 minus square root of 5 squared. 1 plus 1 plus 5 square root of 7. So to get our answer, which is square root of 7, we have to do a few things. We have to set up this distance function. We have to find the location of the critical point. We determined it was a minimum just to check, and then we ran through here. And so that's ultimately how we get there. Okay, and that's the idea. You want to solve that type of problem. This actually comes up a lot. So what you'll find is some sort of, imagine if you have a helicopter and it's in a location and there's a mountain, and you can kind of describe the mountain in terms of some sort of surface definition. And you might want to figure out what's the straight line distance from the helicopter to the mountain. And this methodology will not only get you the location in the world space that is the closest, it'll tell you that this is really probably what you need in a real world situation. This just happens to tell you what that distance is. All right, well, let's continue. In this case, we have something that's a little more mathy, a little less tied to a real world scenario, but it could be. It says 3 positive integers whose sum is 30 and sum of the squares is a minimum. So what we need to do for this is we need to construct a couple of equations, so like a word problem. Well, it says that there's 3 positive integers whose sum is 30. So we're going to say x plus y plus z equals 30. Now we need to be careful because technically this is 3 positive integers, so you really should do something weird like take the square root of x squared so that you can guarantee that it's positive there. But let's try it without doing that and see if we can come up with the answer without having to do something so particularly careful. And it says that the sum of their squares is a minimum. So what I'm hearing is that we're trying to construct a function, or the function we're trying to minimize is the sum of their squares. But if we solve this for z, we can then set this up and then we can multiply this out. We can get x squared plus y squared plus 900 minus 60y minus 60x minus 60y plus x squared plus y squared plus 2xy. All right, all that together will get us, so then we can set up some sort of function of just x and y, which will make our lives easier because we won't have to worry about partials with respect to z. That'll give us 2x squared plus 2y squared plus 2xy minus 60x minus 60y plus 900. All right. Now, I should have said this beforehand, but if we had three positive integers whose sum is 30, what you probably recognize is that we could have just run through all the possibilities, right? There's 1, 1, 28, 1, 2, 27, 1, 3, 26, and then you could keep on going. You could do 5, 7, 18, right? You could check all of them and then check their sum of the squares and see which one's minimized. But that's a problem that takes too long. And so we want to do this to try to short circuit that. But just know that fallback is there in case we need to check anything. So if we get this partial with respect to x, get 4x plus 2y minus 60. Partial with respect to y, 4y plus 2x minus 60. So in this case, we don't have x and y by themselves, so we need to set each one equal to 0. Because we're trying to solve for critical points. So solving this for y, what we get is, I'm going to do this a little more opposite than what you might think. I'm going to say 4y equals negative 8x plus 120. That way I can sub into here and say negative 8x plus 120 plus 2x minus 60 equals 0. So that gives me negative 6x plus 60 equals 0. X is 10. Plugging that back in here, we get y is also 10. Plugging that back in here, z is also 10. So then you might have to ask yourself, did I get a maximum or did I get a minimum? Well, there's a couple of ways to check that. You could say, all right, what about the case where if this is going to be a maximum or it's going to be a minimum? So by checking some other value, we're going to be able to see what it was. So if I say, 1, or rather, let's do something simple. 5, 5, 20. So if I take f here, f of that, I get 25 plus 25 plus 400. I get 450. If I take f of 10, 10, 10, I get 100 plus 100 plus 100 equals 300. So what that tells me is that since this value is larger than this must be the minimum. And that's how we solve some applications using Extrema.